Have you ever wondered why you can melt a plastic bottle and recycle it, but you can't do the same with the plastic on your light switch? They're both called plastic, right? But one softens with heat and the other just burns. What's going on here? The answer lies in how these materials are built at a molecular level, and it's one of the most fundamental ways we classify polymers. In this video, we're going to break down the classification of polymers based on their thermal behavior. That's a fancy way of saying how they react to heat. By the end of this, you'll understand the crucial difference between the two major types, thermoplastics and thermal setting polymers. We'll cover what they are, a simple analogy to remember them forever, how they look on a molecular level, and where you see them every single day. Let's get started. First up, we have thermoplastics. Let's start with the official definition. So, what does that really mean? Think of a thermoplastic like a stick of butter or wax. You can heat it up and it melts into a liquid. You can pour that liquid into a mold, and when it cools down, it becomes solid again. The best part? You can repeat this process over and over and over. The butter doesn't fundamentally change. This happens because the long polymer chains in thermoplastics are held together only by weak intermolecular forces. When you add heat, you give the chains enough energy to overcome these weak forces and slide past each other. It's like a bowl of cooked spaghetti. The strands can move around freely. Visually, imagine this. The heat just gives them the freedom to move. When it's gone, they get locked in their new shape. No permanent chemical change occurs. This is the key. So where do we see these? Everywhere. Your plastic water bottle is likely made of PET or polyethylene terephthalate. Your food containers, car bumpers, and toys are often made of polypropylene. The white pipes used in plumbing are PVC or polyvinyl chloride. Because this heating and cooling process is reversible, thermoplastics are generally highly recyclable. That's why you can melt down old bottles to make new products. Okay, so if thermoplastics are like reusable wax, what's their opposite? That brings us to our second category, thermosetting polymers, or simply thermosets. Let's look at the textbook definition first. Irreversible, permanent. What does that mean in simple terms? Think of a thermoset like baking a cake. You start with the liquid batter. You put it in the oven, and the heat causes chemical reactions that cook it into a solid sponge cake. Now, can you turn that cake back into liquid batter by heating it again? Of course not. You'll just end up with a burnt cake. That's exactly how thermosets work. During the initial heating or curing, strong permanent chemical bonds called crosslinks form between the polymer chains. They don't just slide past each other anymore. They become locked together in a rigid 3D structure. Let's visualize what's happening. Those crosslinks are like superglue, locking everything in place forever. Once they form, you can't break them without destroying the entire polymer. You find thermosets in applications where you need high strength and heat resistance. Remember that electrical switch from the beginning? It's made of a thermoset called Bakelite. You want it to resist heat, not melt. Other examples include the strong epoxy resin you use as an adhesive, the durable laminates on kitchen countertops, and the hard casing for electronics. These materials need to hold their shape and stay strong even when things get hot. Let's put them side by side for a quick comparison. Okay, time for a quick quiz. Let's apply what we've learned. How would you classify the polymer phenol-formaldehyde? Let's think it through. First, you might recognize phenol-formaldehyde by its common trade name, Bakelite. Now, where do we see Bakelite? We already mentioned its use for electrical switches, old telephone casings, and handles for pots and pans. What do all these things need? They need to be rigid, strong, and most importantly, heat resistant. The last thing you want is your pot handle melting while you're cooking. This property of becoming permanently hard and resisting heat is the defining feature of a thermosetting polymer. So, the answer is
Phenol formaldehyde is a classic example of a thermoset. Simple as that. So let's wrap it all up. The next time you look at a plastic object, ask yourself a simple question. Can it be melted and reshaped, or is it permanently hard? If it's like wax, something you can melt and reuse like a plastic bottle, it's a thermoplastic. And if it's like a cake, something that's been baked into a permanent shape like an electrical switch, it's a thermoset. It's all about whether the change is reversible or irreversible. If this video made this concept click for you, do us a favor and hit that like button and subscribe for more engineering topics made simple. Got a question or another topic you want to see broken down? Let us know in the comments below. Thanks for watching.